Hello everyone, this is Hamada Risk. Today I'm going to talk about indoor localization using solar cells. This is a joint work with Dongma, Mahbub Hassan, Mustafa Yusuf. This is our agenda for today, and I will start with the introduction and the basic idea, followed by the proposed system details. Then I will show the evaluation and the experimental results. Finally, I will conclude my presentation. As people spend most of their time indoors last couple years due to COVID, we have witnessed an ever-growing demand for accurate and ubiquitous indoor positioning system in many applications, including contact tracing due to COVID or tracking of elderly people who are living alone or 911 services and so on. The criteria for the end localization system is to be accurate enough for indoor settings and comes with low cost and easy to deploy. And finally, but most importantly, to be energy efficient and doesn't consume much energy or even has zero energy consumption profile. So the state-of-the-art localization system can be in general categorized into Wi-Fi based localization, which are widely adopted for indoor localization. However, this solution usually requires a high density of access points and also mobile device with Wi-Fi support. Wi-Fi systems in general consume non-negligible amount of energy from the mobile device or for powering the Wi-Fi access point. On the other hand, light-based systems leverage the high density of light sources in the indoor environments to localize the user by using smartphone cameras or light sensors. So this limits the applicability of such applications because they require the user to continuously scanning for the light. And this leads to high power consumption, which drains the smartphone's battery so quickly. Recently, there has been a trend of fitting many indoor IoT devices with solar cells to extend their battery life or enabling completely battery-free operation. The number of devices powered by solar cells is increasing, including smartwatches, smart calculators, and so on. The market size of solar cells is growing, exceeding 100 million USD per year. Inspired by this, we propose a PVDeepLoc, a novel device-free, energy-free, light-based indoor localization system that passively leverages photovoltaic currents generated by solar cells distributed in the environment. The system doesn't require the user to wear or carry any device. Also, the system not only consumes zero energy, but also harvests energy and power other devices. The PVDeepLoc effectively trains a deep network for estimating a fine-grained user location, leveraging regularization and data augmentation techniques, leading to a more accurate and resilient model. We deployed the system in a real-world testbed. So the basic idea is to use solar cells to convert the energy of light into electrical energy through the photovoltaic effect. So the amount of generated energy is usually measured by the photocurrent, which is affected by different factors, including the intensity of the received light. Therefore, the light received by solar cell may be blocked when the user is in the proximity of the cell, and thus the generated photocurrent will decrease. In this vein, when multiple solar cells are exploited, a specific human location will leave a unique signature on the photocurrent signals from different cells. So we can construct a fingerprint dataset of photocurrent measurements for different user locations in the environment. This data will enable training a model for fine-grained human localization purposes while ensuring energy harvesting by solar panels. This is a system architecture consisting of two different stages, an offline training stage and online tracking stage, and I'm going to discuss each module in the following slides. So the system starts by the data collection module that records photocurrent measurements at different predefined reference points in the area of interest. For capturing these measurements, each solar cell is connected to an analog to digital converter whose output is fed to a Raspberry Pi module, and the HTTP request is sent to the installed Raspberry Pi to get a response with the photocurrent readings from their connected solar panels. These readings are stored in our fingerprint database. Then the photocurrent values are further processed by this module in order to generate a unified fixed size feature vector where each entity represents a reading from a corresponding solar cell. Then the feature vector is rescaled to the range of 0 to 1 due to the neural network sensitivity to the input scales. And then the system employs augmentation techniques to generate synthetic data that reflect the typical variation in the measurements at runtime, and also avoid overfitting problem which may occur due to training with small amount of data. After deployment, permanent or temporary blocking of line of sight to some solar cells may occur. This may lead to an overall deterioration of the system performance over time. So we train the localization model in a way that reduces the dependency on all solar cells in the input. This is realized by generating new samples where some solar cells are randomly excluded or simply their photocurrent are set to zero. In effect, the localization model can be trained with different views of the input, leading to a more robust localization that is less affected by the environment dynamics. Also, temporal variations of light intensities received at each solar cell may negatively affect the localization performance. Therefore, we propose the perturbation method that adds noise to the original photocurrent vector. Then we train a localization model with these noisy samples. This has the effect of smoothing the boundaries of the underlying distribution of photocurrent, leading to more robust localization. To build a deep model, we train a fully connected neural network with an input of photocurrent measurement from the solar cells, and the output layer consists of a number of neurons corresponding to the reference points. So the network operates as a classifier, yielding a probability distribution over the reference grid. The reference grid with the maximum probability is considered the predicted location. Dropout regularization is employed here to increase the model robustness against overfitting by randomly excluding neurons during the training, preventing them from co-relying on each other. We deployed our system in a room of 2 by 3 square meters and with a number of grids equal 24 and interspacing between points of 0.5 meters and sampling rate 3 hertz, 4 installed solar panels, and the efficiency of each panel is 15.5%. The dimension of each solar panel is 10 by 7 centimeters with 8 light lamps of 450 lumens each, as shown in the figure. And the data collected while the user is standing at the center of each grid. The system localization performance is evaluated by calculating the Euclidean distance error between the ground truth location and the estimated user location. And the reported results confirm the good performance of the system, achieving as low as only 0.6 median error and the 7th percentile of 1.1, and the maximum error is 1.8 meter. We also studied the impact of the density of solar cells on the performance of the system. The figures show that the more solar panels available, the richer input information provided to the localization model, and thus better localization accuracy. However, even with density as low as 2 cells, the system can achieve an accurate room-level localization with less than 2 meter median error. This is due to the light perturbation caused by the user presence, which can be measured by the installed few solar cells. In conclusion, we presented the PVDeepLoc, an accurate and robust device-free, energy-free indoor localization system that uses photocurrent measurements of solar cells to localize users passively without requiring users to wear or carry any device. PVDeepLoc trains a deep neural network to estimate the fine-grained user location, and the system employs different regularization techniques to enable effective use of deep learning that has a better generalization ability and avoid overfitting. We also implemented the system in a real-world testbed, and the results showed that we can achieve a median localization accuracy of 4.6 meters. And currently, we are extending the system in different directions by studying the variation in the number and type of light sources, including dimmable and outdoor light coming from windows, and improving the system robustness against environmental changes and variation in reflectivity of different objects. Thank you so much for your attention. I would be happy to receive your questions.